In this video, we're going to go over the properties of convergent sequences. So if you suppose that you have AN and BN, two convergent sequences, and C is a constant, then we're going to have the following rules for convergent sequences. The first one is the sum rule, which is if the limit when it goes to infinity of the sum of the two sequences is just going to be the sum of the two limits. Similar with the difference, the limit of the difference of the two sequences is just going to be the difference between the limits. Similar thing happens with the product, and the limit of the product of two sequences is going to be the product of the limits. Now, for the quotient, we have the same thing, but we gotta make sure first that the limit of the denominator is not zero. So in this case, if we have limit of AN over BN, we gotta make sure that the limit when it goes to infinity of BN is not zero. And if that happens, then we can kind of say, oh, okay, so the limit of the quotient is the quotient of the limit. Another of the important rules is going to be that if I have a constant that is multiplying the sequence, I can kind of pull the constant out of the limit. This is consequence of really the limit properties. And so we have this also as well for sequences. Similar is the power rule, that if we have a power of a sequence and we take the limit when it goes to infinity, it's equivalent just to take the power of whatever the limit is, since a power is a continuous function. Now, one of the examples that we saw on the last video had to do with the squeeze theorem. And that what happens in there is that if you have three sequences, so that this setup happens where AN is less or equal than BN and less or equals than CN, and then we have that the limits when n goes to infinity of the extremes are the same. So the limit when n goes to infinity of AN is equals to the limit when n goes to infinity of CN. Then we're going to have that the limit of the middle sequence has to be the same. And so the way that we can see this is as this picture showcases. Here we have that BN is being squeezed by AN and CN. And because AN and CN, they're going to this limit L, then also BN is also going to go to that limit L. Now, the final two properties will be the property of the absolute value. So we have that the limit of the absolute value is 0, then the limit of the sequence is 0. This is going to be especially useful for when we have alternating sequences, where we can analyze the limit without really having to pay attention to the alternating pace. Also, if continuous functions are involved with the sequences, and we have that the limit when n goes to infinity of a sequence is L, and f is a continuous function, then we have that the limit when n goes to infinity of f of the sequence is going to be f of the limit. So we can kind of play with multiple properties in here. It's not only going to be the power, but we can also have a square root, exponential, logs. We have a bunch of other functions that we can use here with the limits of the sequences. So one of the examples that we can examine is the sequence r to the n. So if you consider r to be a real number, we can see how the sequence r to the n work. Initially, if r is equals -1, then you're going to have an alternating term that bounces from -1 to 1, -1 to 1, -1 to 1. And so, of course, that is a divergent sequence because that's never going to go anywhere. And you can see that showcased in this first picture in the left. Now, when r is 1, then of course it's not going to be interesting either, because it's just going to be simply be 1. And all the points are going to be 1. So you can see that in the middle sequence on the black dots, that's when r is equals 1. Regardless of what the power is, it's always going to be equals to 1. Now, if r is bigger than 1, though, that's going to be power. There's going to be an exponential here. and it's going to grow to infinity. And so that's going to be a divergent sequence. And if R is between 0 and 1, then that's one of the scenarios where we can actually say that that's going to be a convergent sequence. It's actually going to go to 0. And so we can kind of analyze that. We can kind of tell the two different cases that are going to come up with this. And is that if R is bigger than 1, then the limit of R to the n is infinity. And if the absolute value of R is between 0 and 1, then the limit when n goes to infinity of R to the n is equal to 0, and the sequence is convergent. Notice that I make the mention of the absolute value of R, because you can also have R being a number between -1 and 0. And so that also will be a convergent set of points, but it will be negative. So that's why I care about, or I put the absolute value to just cover the two cases. Now, when another property that is common when we have convergent sequences, or conversely, some properties that are going to point towards a convergency sequence, is the monotone unbounded properties. So first, what is monotone? If we have a sequence that is increasing, so that means that the successor term is always bigger than the term before, then we're going to have that is an increasing sequence. In the increasing sequence, you're going to have this behavior where A2 is bigger than A1, but A3 is bigger than A2, but A4 is bigger than A3. And in general, AN is going to be bigger than AA minus 1. That's an increasing sequence. Similarly, you can also have the decreasing sequence. In that case, the successor term is always going to be smaller than the one that came before. So in this scenario, A1 is bigger than A2, A2 is bigger than A3, is bigger than A4, and so on and so forth. And the first one is always going to be bigger than AN. These kind of sequences, whether increasing or decreasing, are being going to call monotone. And when we have a monotone sequence, then we can see that it's either increasing or decreasing towards a certain value. Or that value can be a fixed constant, or it can be just infinity or minus infinity, depending of it's increasing or decreasing. Now, what is gonna make an increasing or decreasing function, or sequence, convergent is if we can have that is bounded. And so a sequence is bounded above if it exists a number m, so that an is always less than that number m for all n bigger than 1, and is bounded below if it exists a number that is so that the sequence is always bigger than that number for all n bigger than 1. A sequence that is bounded above and below is going to be simply called bounded. And so when we have these two things together, bounded and monotone, then that's going to imply convergency. So every bounded monotonic sequence is going to be convergent. Notice that this is an example here. We have an increasing sequence, but it's going to be bounded by certain value. That value is going to be called m. So because it's bounded, it says that it's never going to go beyond that point. So it means that at some point when n is large, all the values of a sequence are going to go very close to a certain number L. And so that anticipates that precisely a limit is going to exist, and so the sequence will be convergent. So now let's see some examples of this into play. We're going to be using certain sequences. So we're going to use an equals 1 over 2 to the n. We're going to use bn equals 1 over n. We're going to use cn minus 1 to the n. And we're going to use dn equals e to the n. Now I'm going to use c for convergent and d by divergent. Notice that an is convergent, bn is also convergent. Both of this, they go to 0 under limits. Now cn is divergent because the limit does not exist. And dn is also divergent because the limit goes to infinity. So this is two divergent, two convergent sequences. So now, because of what we have, we're going to have that the limit when x goes to infinity of an plus bn is just going to be the limit when n goes to infinity of an plus the limit when n goes to infinity of bn. So we're using the properties of the limits. And this is just going to be 0 plus 0. And so the limit of the sum is 0. Now, this is the first one. Now, for the second one, we have a ratio. But there's an issue here. So we have that the limit when an over bn, this is do not exist. Why? Because the limit when n goes to infinity of bn is 0. So I cannot make a ratio. I cannot make this ratio. Okay? Now, if I do limit when n goes to infinity of an times cn, so limit when n goes to infinity of an times cn, what I'm really doing is limit when n goes to infinity of minus 1 to the n times 1 over 2 to the n. And so this now transforms into an alternating sequence. But remember that I can use the fact that the limit when n goes to infinity of the absolute value is 0. And so that is going to imply that the limit of this is going to be 0. So the absolute value of this is just limit when n goes to infinity of 1 over 2n, and this is just 0. So that implies that the limit of the whole sequence is 0. And so that's the use of that property there. Now let's go to the next one. Now we're going to consider limit when n goes to infinity of 7 over 1 over 2 to the n. Notice that this is just going to be 7 the limit by properties of the sequences. And because this is 0, then this is just going to be 0 times 7, which is 0. So not very interesting result in there. Okay. Now the difference between an and dn. So this is a limit when n goes to infinity of 1 over 2n minus limit when n goes to infinity of dn. But the thing is that this is infinity. So this means that everything is infinity. And this just is going to be divergent. This difference of sequences here is just going to be divergent. If one of them is divergent, then both of them in the difference are divergent. Now we're going to have limit when n goes to infinity of cn minus dn. So we're testing what happens when we have the limit between these two sequences, a difference, but we have minus 1 to the n minus e to the n. The problem here is that the limit when minus 1 to the n does not exist. So it doesn't matter that this is infinity. In general, it's not going to exist. It's not going to be infinity. It's just it did not exist because one of the pieces does not exist. So overall, it doesn't exist. Now, for the product between an and cn, so we have an and cn. I think I did this one before. Yeah, I did this one before, so I'm not gonna do it again. Yeah, instead, let me go with an times 3 to the n. So an times 3 to the n is really doing the limit when n goes to infinity of 3 to the n over 2 to the n. We actually saw that one in the previous video. We saw that this was infinity, so this new sequence here will be divergent. Similar with where we have in the last possible limit, we have, or let's actually see. Dn is e to the n, but now we're dividing by n to the n. So notice that in this case, actually n to the n grows faster than e to the n. So this limit is going to be 0. And if I have a sequence Cn being e to the n over n to the n, that sequence will be also convergent. Okay? So that's some calculations using the properties of the limit. Now, last but not least, we want to discuss if the sequences are bounded or monotone. And so for that, let me go back up here and just make a discussion about this. Notice that an is equals 1 over 2 to the n. So this is like 1/2. This always is going to be less than 1. The absolute value of this is less than 1. Because it's always a value less than 1. So this is bounded. Now, if you start looking at the terms, a1 is 1/2, then a2 is 1 over 4, then a3 is 1 over 8. So this is actually decreasing. It's decreasing in value every time that we take an n. So this is a monotone sequence as well. So this is another way of proving that this is convergent. It is bounded and is monotone, so that applies, and I don't have to take the limit. I can just argue by these two things that this sequence is convergent. Now for Bn, I have a similar situation. Bn is 1 over n, is also going to be less than 1. And so is bounded. And it's also going to be monotone because take a look at the terms. We have 1 over 1, 1 over 2, 1 over 3, 1 over 4. Every time is decreasing the value. So this is decreasing. And so we have decreasing in monotone, then we have that is convergent. We already knew it was convergent, but we're just double checking with these conditions. Now, C and D are a different situation. Notice that Cn, the absolute value of Cn is actually 1. So this is bounded. But it's not monotone. It doesn't increase. Like A1 is 1, or A1 is minus 1, A2 is 1, A3 is minus 1 again. So it doesn't grow. It just jumps from one value to the other. So that will not be monotone, and that's why it's not convergent. Dn is not bounded. It's actually increasing all the time. Every time it's a larger value. So it's all the time growing. It's growing to infinity. So clearly it's not bounded, but it is increasing. But that's why it's divergent, because it increases all the time. It goes to infinity. It has no bounds. Okay? All right, so that is the end of the examples that we have for properties of the convergence sequences.